Hello there, and welcome to Whispered Knowledge. I'm so glad you found your way here tonight. Maybe you've had a long day, or perhaps you're simply drawn to the gentle rhythm of deep thoughts and natural wonders rather than counting sheep. Either way, tonight's journey is crafted just for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as we drift together into the world's greatest frontier. Because tonight, we aren't simply learning about water. We're exploring the ocean, that vast blue realm that covers most of our planet, holds most of its mysteries, and sustains most of its life. The ocean is not one thing, but many. It is sunlit shallows and crushing depths, warm currents and frozen plains, bustling reefs and silent trenches. It shapes our weather, regulates our climate, and provides the very air we breathe. And yet, despite covering over 70% of Earth's surface, it remains largely unknown to us. Less than 20% has been mapped and explored, making the ocean one of the final frontiers. Not in space, but right here beneath the waves. Over the next while, we'll drift through 100 facts about this extraordinary realm. Some will surprise you, some will spark quiet wonder, and some may simply settle into your thoughts as you drift off to sleep. We'll journey from the sun-drenched surface to the deepest trenches, from coral gardens teeming with color to dark waters lit only by living light. We'll meet creatures stranger than fiction and discover systems more complex than any machine. And before we begin, if these calm explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to Whispered Knowledge. It helps others find their way here too, one curious soul at a time. Now, let's begin our descent into the blue. The vast blue realm, understanding our ocean. The ocean covers more than 70% of Earth's surface. When you look at our planet from space, the overwhelming impression is blue, a water world wrapped in swirling clouds. This isn't just aesthetically striking, it's fundamental to everything about our planet. The ocean holds about 97% of all water on Earth, making it the dominant reservoir in the global water cycle that drives weather, climate, and the distribution of life itself. But the ocean's reach extends far beyond simple coverage. Its average depth is approximately 3,720 meters, about 12,200 feet, though this varies dramatically from place to place. In some areas, shallow continental shelves extend gently from the shoreline, barely dropping below 200 meters. In others, the seafloor plunges into trenches that descend nearly 11,000 meters, deeper than Mount Everest is tall. The deepest point we know of is the Challenger Deep in the Mariana Trench, located in the western Pacific Ocean. It reaches down approximately 10,924 meters, nearly 11 kilometers beneath the waves. If you could somehow place Mount Everest, with its peak at 8,849 meters, into the Challenger Deep, more than 2 kilometers of water would still cover its summit. The pressure at these depths is crushing, more than 1,000 times the atmospheric pressure at sea level, equivalent to about 8 tons pressing down on every square inch. We often speak of the ocean as singular, but technically, Earth has 5 named oceans. The Pacific is the largest and deepest, covering more area than all the continents combined. It holds more than half of the free water on Earth and contains the Mariana Trench. The Atlantic is the second largest, separating the Americas from Europe and Africa and playing a crucial role in global ocean circulation. The Indian Ocean lies mostly in the southern hemisphere between Africa, Asia, and Australia. The Southern Ocean encircles Antarctica, its cold waters driving important circulation patterns. And the Arctic Ocean, the smallest and shallowest, sits atop the world, largely covered in sea ice. Yet these named oceans are not truly separate. They form one continuous body of water, a global ocean connected by currents, tides, and the ceaseless mixing of salt water that has flowed across our planet for billions of years. Water molecules that evaporate from the Pacific might fall as rain over the Amazon, flow through rivers to the Atlantic, and eventually make their way to the Indian Ocean in an endless cycle of movement and exchange. The ocean contains about 99% of the living space on our planet. This is a staggering fact when you really consider it. The thin biosphere on land, where forests grow and animals roam, represents only a tiny fraction of the space where life can exist. The ocean, with its three-dimensional vastness extending from surface to seafloor across 2/3 of the planet, provides an incomparably larger arena for life. And life has filled it, from the sunlit surface to the darkest trenches, from warm tropical waters to the frozen seas beneath polar ice. Life began in the ocean approximately 3.1 to 3.4 billion years ago. For most of Earth's history, the ocean was the only place where life existed. Land-dwelling organisms didn't emerge until about 400 million years ago, a relatively recent development in the grand scope of geological time. The ocean cradled the first cells, nurtured the evolution of complex organisms, and served as the stage for nearly all of life's major innovations before anything crawled onto land. The ocean holds more carbon than the atmosphere and all terrestrial ecosystems combined. Approximately 37,700 gigatons of carbon are stored in the ocean, compared to about 2,000 gigatons on land. Most of this carbon stays locked away for thousands of years in deep ocean waters, preventing excessive buildup of carbon dioxide in the atmosphere. This makes the ocean one of our most important allies in regulating Earth's climate, acting as a massive buffer against rapid atmospheric changes. But the ocean doesn't just hold carbon passively. Through photosynthesis by phytoplankton, tiny, single-celled plants that drift in surface waters, the ocean produces more than 50% of the oxygen in our atmosphere. Every second breath you take comes from the sea, generated by microscopic organisms you'll never see, but upon which all terrestrial life depends. These phytoplankton form the base of the marine food web, supporting everything from tiny zooplankton to the largest whales. The ocean is also remarkably salty. On average, seawater is about 3.5% salt, roughly 35 grams per litre, or about 7 teaspoons in every bucket of seawater. This salt comes primarily from rocks on land, dissolved by rain and carried to the sea by rivers over millions of years. But salinity isn't uniform across the ocean. In areas where fresh water from melting ice dilutes the seawater, or where rainfall is heavy, salinity decreases. In hot regions where evaporation is intense, such as the Mediterranean or the Red Sea, salinity increases, sometimes reaching over 40 grams per litre. This variation in salinity plays a crucial role in ocean circulation. Combined with temperature differences, salinity helps create density gradients that drive the deep ocean currents we'll explore later. Saltier, colder water is denser and sinks, while warmer, fresher water is lighter and rises. This continuous dance of sinking and rising water masses creates a global circulation pattern that moves heat, nutrients, and dissolved gases throughout the ocean. The ocean is also ancient beyond our usual comprehension. While the modern ocean basins are relatively young in geological terms, some less than 200 million years old, due to the constant recycling of oceanic crust through plate tectonics, water has covered most of Earth's surface for over 4 billion years. The water molecules themselves have cycled through the ocean atmosphere, ice, and life countless times. The water you drink today might have once been part of a primordial ocean, later incorporated into a dinosaur, frozen in a glacier, fallen as rain over a rainforest, and now sits in your glass, ready to continue its endless journey. Understanding the ocean requires thinking in scales both intimate and vast. From the microscopic algae that produce our oxygen to currents that span entire ocean basins, from the chemical composition of a single water molecule to the global cycles that connect every part of our planet, the ocean is not just a feature of Earth. In many ways, it is Earth, the fundamental medium that makes our living planet possible. A vertical journey, the ocean's zones. If you were to sink slowly from the ocean's surface down to its deepest point, you would pass through distinct zones, each defined by light, temperature, pressure, and the forms of life that have adapted to survive there. These zones aren't separated by hard boundaries, but by gradual transitions. Yet each possesses its own character, its own strange beauty, and its own inhabitants perfectly suited to the extreme conditions they call home. Let's begin at the surface, in the sunlight zone, also called the epipelagic zone. This layer extends from the surface down to about 200 meters, roughly 650 feet. Here, sunlight penetrates with enough intensity to fuel photosynthesis, making this the ocean's most productive layer. The warmth of the sun heats the surface, creating a wide range of temperatures from near freezing in polar regions to over 30 degrees Celsius in the tropics. This zone teems with life. Phytoplankton drift in vast blooms, sometimes visible from space as green or blue, swirls across the ocean's surface. These microscopic plants are eaten by zooplankton, tiny animals that in turn feed small fish. Those fish are eaten by larger fish, and so the food web extends upward to apex predators like sharks, tuna, and dolphins. Sea turtles paddle through warm currents. Jellyfish pulse gracefully. Seabirds dive from above, plunging into schools of fish. The sunlight zone is the ocean most of us know, the realm we swim in, surf in, and boat across. It's where coral reefs grow in tropical waters, where kelp forests sway in temperate seas, and where the majority of commercial fishing occurs. But it represents only a tiny fraction of the ocean's total volume. Below this sun-drenched layer lies something stranger and more vast. Descending past 200 meters, you enter the twilight zone, or mesopelagic zone, which extends down to about 1,000 meters, around 3,280 feet. Light still penetrates here, but only barely. By the time sunlight reaches these depths, it has been filtered and scattered by the water above, until only the faintest blue glow remains. There is enough light for some organisms to see, but not enough for photosynthesis. The twilight zone is populated by creatures adapted to dim light and increasing pressure. Many have large eyes to capture every available photon. Others have developed bioluminescence, the ability to produce their own light through chemical reactions in specialized organs. Fish with names like hatchetfish and lanternfish blink and glow in the darkness, using light to communicate, attract prey, or confuse predators. Temperature drops significantly in the twilight zone. While surface waters might be warm and pleasant, here the temperature hovers around 4 to 10 degrees Celsius, cold enough that most warm-blooded visitors would struggle without protection. Yet, life is abundant. Scientists estimate that about 90% of the world's fish by weight live in the mesopelagic zone, about 10 billion tons of fish. The bristlemouth fish alone may number about a quadrillion individuals, making them the most numerous family of vertebrates on Earth. These fish and other twilight zone inhabitants play a crucial role in the ocean's ecology. Many species make a daily vertical migration, rising toward the surface at night to feed on plankton under cover of darkness, then descending back to the depths during the day to avoid predators. This migration, involving trillions of small animals, represents the largest movement of biomass on the planet, occurring every single day in oceans around the world. Continue downward past 1,000 meters and you enter the midnight zone, the bathypelagic zone, extending from 1,000 to 4,000 meters depth. Here, no sunlight penetrates at all. The only light is that produced by the creatures themselves, bioluminescent flashes and glows in otherwise total darkness. The water is perpetually cold, hovering around 4 degrees Celsius, just above freezing. Pressure in the midnight zone is immense, ranging from 100 to 400 times atmospheric pressure at sea level. Most organisms with gas-filled spaces, like lungs, would be crushed instantly. Yet the creatures here have adapted, their bodies lacking air spaces, their cellular chemistry adjusted to function under enormous pressure, their metabolisms slowed to conserve energy in an environment where food is scarce. Strange fish drift through the darkness. Anglerfish dangle glowing lures to attract prey. Viperfish sport enormous teeth. Gulper eels possess hinged jaws that can open wide enough to swallow prey larger than themselves. Many of these creatures are small and slow-growing because food is so scarce. They survive on marine snow, a constant gentle rain of organic debris, dead organisms, fecal pellets and other particles that drift down from the productive layers above. Descending further, past 4,000 meters, we reach the abyssal zone, the abyss itself, extending from 4,000 to 6,000 meters depth. The name comes from a Greek word meaning no bottom, and for centuries, people believed nothing could survive here. 3/4 of the ocean floor lies within this zone, vast plains of soft sediment stretching for thousands of kilometers in near total darkness. The abyssal zone is remarkably uniform in its conditions. Temperature is near freezing, usually between 0 and 3 degrees Celsius. Pressure is crushing, over 400 times atmospheric pressure. Food is incredibly scarce, limited mainly to whatever marine snow makes the long, slow drift down from above. And yet, life persists. The seafloor is home to sea cucumbers, brittle stars, tube worms, and countless microorganisms. Small fish and octopuses patrol the sediment. All are adapted to cold, darkness, and intense pressure, living slow, patient lives in one of Earth's most extreme environments. Finally, in the deepest ocean trenches, below 6,000 meters, lies the Hadal Zone, named after Hades, the ancient Greek god of the underworld. This zone exists only in deep trenches, steep depressions in the seafloor, where tectonic plates collide and one is forced beneath the other. There are about 13 oceanic troughs and 33 trenches that reach Hadal depths, scattered across the ocean floor like scars. The Hadal Zone was once thought to be lifeless, too extreme for even the hardiest organisms. But deep-sea expeditions have revealed an abundance of resilient and bizarre life. Hadal snailfish, pale and gelatinous, lack swim bladders and have enzymes adapted to function under extreme pressure. Amphipods, shrimp-like crustaceans, grow to remarkable sizes, some reaching over 30 centimeters long. Comb jellies drift through the darkness. Sea cucumbers crawl across the sediment, processing organic matter. More people have been to the moon than have descended into the Hadal Zone. It is humanity's least explored place, a dark, remote, and hostile environment that challenges our technology and our understanding of what life can endure. The pressure in the deepest parts of the Mariana Trench exceeds 1,000 times atmospheric pressure, equivalent to having about 50 jumbo jets stacked on top of you. And yet, even here, life continues. Bacteria thrive in the sediment. Larger organisms find ways to survive and even reproduce. The Hadal zone reminds us that life is more resilient, more adaptable, and more persistent than we often imagine. It colonizes every available niche, no matter how extreme, finding ways to extract energy, build bodies, and pass on genes in conditions that seem impossible. This vertical journey through the ocean's zones reveals a layered world of decreasing light and temperature, increasing pressure, and ever-present life. Each zone has its own ecology, its own cast of characters, its own rhythms and patterns. Together they form a continuous column of water connecting the sunlit surface to the darkest abyss, a gradient of conditions spanning the full range of what our planet can offer. Rivers in the sea, ocean currents and circulation. The ocean is never still. Beneath its surface, invisible to the eye but powerful beyond measure, great currents flow like rivers in the sea. These currents move water, heat, nutrients, and life itself across thousands of kilometers, connecting distant regions and shaping the climate of entire continents. Understanding ocean currents is understanding the ocean's heartbeat, the ceaseless circulation that keeps the whole system alive. Ocean currents are driven primarily by two forces: wind and density differences. Surface currents, the ones we encounter most often, are driven mainly by wind. As wind blows across the ocean's surface, it drags the water along, creating currents that flow in predictable patterns. The trade winds in the tropics push water westward. The westerlies at mid-latitudes push water eastward. These wind patterns, combined with the rotation of the Earth and the positions of continents, create large circular currents called gyres in each ocean basin. The Gulf Stream is perhaps the most famous surface current. It begins in the Gulf of Mexico, flows through the Strait of Florida, and races northward along the eastern coast of the United States, carrying warm, tropical water toward higher latitudes. At its peak, the Gulf Stream moves more water than all the rivers on Earth combined, transporting heat northward at a rate that moderates the climate of the eastern United States. And, as it continues across the Atlantic, as the North Atlantic Current warms the climate of Western Europe. Without the Gulf Stream and North Atlantic Current, Great Britain and Scandinavia would be far colder, more like the frozen landscapes of similar latitudes in Canada. The current brings warmth and moisture, creating milder winters and sustaining ecosystems that would otherwise struggle to survive so far north. It's a reminder that ocean currents don't just move water, they shape weather, agriculture, and human civilization itself. But surface currents, impressive as they are, represent only part of the ocean's circulation. Beneath the surface lies another system, slower but equally powerful, driven not by wind but by differences in water density. This is the thermohaline circulation, named from the Greek words for heat and salt, the two factors that determine seawater density. Thermohaline circulation begins in the polar regions, particularly in the North Atlantic near Greenland and in the seas around Antarctica. Here, cold temperatures and the formation of sea ice create water that is both cold and salty. As seawater freezes, it excludes salt, leaving the remaining liquid water even saltier than before. This cold, salty water is denser than the warmer, fresher water around it, and it sinks, dropping down through the water column to the ocean floor. This sinking water has to go somewhere. It flows along the bottom of the ocean, spreading outward from the polar regions in slow, deep currents. In the Atlantic, the sinking water forms North Atlantic deep water, which flows southward along the western boundary of the ocean, eventually spreading into the Southern Ocean, and from there into the Indian and Pacific Oceans. As this deep water spreads across the ocean basins, it slowly rises, mixing with waters above through turbulent processes, driven partly by tides and partly by wind. Eventually, after hundreds or even thousands of years, this water returns to the surface, warmed by the sun and freshened by rain, and begins its journey back toward the polar regions as a surface current, completing the cycle. This global pattern of sinking and rising, deep flow and surface return is often called the ocean conveyor belt. It's a simplified model, but it captures the essential idea. The ocean circulates not just horizontally in surface gyres, but vertically, in a grand overturning that connects the surface with the abyss, the equator with the poles, and the Atlantic with the Pacific. The ocean conveyor belt moves slowly, about 100 times slower than wind-driven surface currents. A single cycle, from sinking in the North Atlantic to rising in the Pacific and returning to the Atlantic, takes roughly 1,000 years. But despite its slow pace, the conveyor belt transports enormous amounts of heat. It carries warm tropical water northward in the Atlantic, releasing that heat to the atmosphere and moderating the climate of northern latitudes. It carries oxygen-rich water to the deep ocean, supporting life in the abyss. It redistributes nutrients, bringing fertility to surface waters where upwelling occurs. Upwelling is particularly important. In certain regions, deep currents are forced to rise toward the surface by the shape of the seafloor or by winds that push surface water away from the coast. When this happens, cold, nutrient-rich water from the depths wells up, bringing with it nitrogen, phosphorus, iron, and other elements that phytoplankton need to grow. These upwelling zones, though they cover only a small fraction of the ocean's surface, support some of the most productive fisheries in the world, from the Peruvian anchovy fishery off South America to the sardine fisheries off California and southwestern Africa. Ocean circulation also plays a crucial role in climate variability. Phenomena like El Niño and La Niña arise from changes in ocean-atmosphere interactions in the tropical Pacific. During El Niño, weakening trade winds allow warm water to spread eastward across the Pacific, suppressing upwelling off South America and altering weather patterns worldwide. During La Niña, stronger trade winds pile warm water in the western Pacific, enhancing upwelling in the east. These oscillations affect rainfall, storm patterns, and temperatures across the globe, demonstrating how intimately connected the ocean and atmosphere truly are. There's growing concern about the stability of the ocean conveyor belt. Climate change is warming the ocean and melting polar ice, both of which reduce the density of surface water in critical regions where sinking occurs. Fresher, warmer water is less likely to sink, potentially slowing the thermohaline circulation. Some climate models suggest that the Atlantic meridional overturning circulation, the Atlantic portion of the conveyor belt, has already weakened by about 15% since the mid-20th century, though uncertainty remains high. If the circulation were to slow significantly or even shut down, the consequences would be profound. Western Europe could experience colder temperatures. Tropical rainfall patterns might shift. Marine ecosystems that depend on nutrient delivery from deep waters could collapse. The ocean's ability to absorb carbon dioxide might decrease, accelerating atmospheric warming. While an outright shutdown is considered unlikely in the near term, the possibility serves as a reminder of how delicate and interconnected our planet's systems are. Ocean currents, both surface and deep, wind-driven and density-driven, are the arteries of the global ocean. They transport heat, nutrients, oxygen, and life itself, connecting distant regions in a web of flowing water that has shaped Earth's climate for millions of years. They are invisible to the casual observer, yet they govern where fish swim, where storms form, where deserts and rainforests exist, and how our climate responds to change. In the ocean's currents, we see not just moving water, but the pulse of the planet itself, a universe of life, marine biodiversity. The ocean is alive in ways that challenge our imagination. From the smallest virus to the largest whale, from simple single-celled organisms to complex societies of intelligent animals, the sea contains a staggering diversity of life. Scientists estimate that over 90% of all life on Earth is found beneath the ocean's surface, making it by far the largest and most biodiverse ecosystem on the planet. Yet despite this abundance, we have classified only a fraction of marine species. About 230,000 species have been formally described and named, but scientists believe there may be 2 million or more yet to be discovered. Some estimates range even higher, suggesting that the ocean could hold 10 million species, most of them microbes and small invertebrates living in places we've barely begun to explore. Consider the numbers. Over 1,700 species of fish have been found in the deep sea alone. The mesopelagic twilight zone contains around 10 billion tons of fish, more biomass than all the fish in surface waters combined. Coral reefs, covering less than 1% of the ocean floor, support approximately 25% of all marine species, earning them the title rainforests of the sea. Marine biodiversity spans an enormous range of forms and strategies. At the smallest scale, viruses and bacteria number in the astronomical millions per milliliter of seawater. A single liter of seawater can contain 38,000 different kinds of microbes, each playing some role in the complex chemistry and ecology of the ocean. These microorganisms cycle nutrients, decompose organic matter, produce oxygen through photosynthesis, and form the base of the marine food web. Phytoplankton, drifting microscopic algae, are responsible for more than half of the photosynthesis on Earth. Though individually tiny, collectively they form vast meadows of green life that bloom and fade with the seasons, visible from space as swirls of color across the ocean's surface. They convert sunlight and carbon dioxide into organic matter, feeding zooplankton, which feeds small fish, which feed larger fish, and so on up the food chain to apex predators. Among the zooplankton drift creatures of remarkable diversity, copepods, tiny crustaceans, may be the most abundant animals on Earth by biomass. Krill, shrimp-like creatures that swarm in Antarctic waters, form the primary food source for baleen whales, the largest animals ever to exist. Jellyfish pulse through the water, some the size of a pinhead, others with tentacles stretching over 30 meters. Salps, barrel-shaped gelatinous filter feeders, can form chains kilometers long, filtering phytoplankton from the water. The ocean's invertebrates display stunning variety. Mollusks, the second most diverse animal phylum after arthropods, include everything from microscopic snails to giant squid with bodies over 10 meters long. Echinoderms like sea stars, brittle stars, sea cucumbers, and sea urchins crawl across the seafloor in slow-motion choreography. Sponges, among the most ancient animals, filter vast quantities of water through their porous bodies. Corals, though they look like rocks or plants, are colonies of tiny animals related to jellyfish, building limestone skeletons that form the architecture of reefs. Fish, of course, are everywhere in the ocean. Over 1,500 species swim among coral reefs. bluefin tuna, among the largest and fastest marine fish, can weigh over 600 kilograms and swim at speeds exceeding 55 miles per hour. The oarfish, the longest bony fish in the world, can reach lengths of over 15 meters, its snake-like body sporting a magnificent red fin along its length, accounting for many historical sea serpent sightings. In the deep sea, fish have evolved bizarre adaptations to cope with darkness, pressure, and scarcity of food. Anglerfish dangle bioluminescent lures to attract prey. Gulper eels can expand their mouths to swallow prey larger than themselves. Hatchetfish have silvered bodies and upward-pointing eyes to see predators silhouetted against the faint light from above. Many deep-sea fish are small and slow-growing, conserving energy in an environment where every calorie counts. Marine reptiles include sea turtles, of which 7 species exist worldwide, 6 of which are found in the waters of the Great Barrier Reef. These ancient mariners have roamed the oceans for over 100 million years, outlasting the dinosaurs and adapting to life in both warm, tropical waters and cooler temperate seas. Sea snakes, highly venomous but generally docile, hunt fish in shallow coastal waters. Saltwater crocodiles and marine iguanas represent the few reptiles that have ventured into the ocean's edge. Seabirds, though they live on land and in the air, depend on the ocean for food. Albatrosses range across vast distances, some flying over 15,000 kilometers in a single foraging trip. Penguins, flightless but superb swimmers, fly underwater at speeds up to 25 miles per hour, chasing fish and krill. Sadly, seabird populations have dropped by about 70% since the middle of the 20th century, pushed toward the brink by overfishing, pollution, and climate change. Marine mammals represent some of the ocean's most charismatic and intelligent inhabitants. Whales, dolphins, and porpoises, collectively called cetaceans, range from the tiny vaquita, barely 1.5 meters long, to the blue whale, the largest animal ever to have lived, reaching lengths over 30 meters and weights approaching 200 tons. The blue whale's heart alone is the size of a small car, and its blood vessels are so broad that a full-grown trout could swim through them. Whales can be divided into 2 groups, baleen whales and toothed whales. Baleen whales, including blues, humpbacks, and right whales, have fibrous plates in their mouths that filter enormous quantities of tiny prey like krill and copepods. Toothed whales, including sperm whales, orcas, and dolphins, hunt larger prey like fish and squid. Sperm whales are recorded as the loudest marine animals, with clicks that can reach 230 decibels, louder than a jet engine, used for echolocation and communication in the deep sea. Seals, sea lions, and walruses, collectively called pinnipeds, meaning fin-footed, are adapted to life both in the ocean and on land. Over 30 species exist worldwide, from Arctic ringed seals to tropical Hawaiian monk seals. Some can dive to extreme depths, over 2,000 meters, and hold their breath for over an hour, hunting fish and squid in the darkness before returning to the surface. One of the ocean's most remarkable features is the prevalence of bioluminescence, the production of light by living organisms. About 90% of animals in the deep sea possess this ability, using it for communication, attracting prey, deterring predators, or finding mates. Dinoflagellates, single-celled algae, light up when disturbed, creating glowing waves at night. Lanternfish flash patterns of light along their bodies. Firefly squid emit brilliant displays of blue light from organs called photophores. The ocean also supports symbiotic relationships of stunning complexity. Coral polyps house algae called zooxanthellae in their tissues, providing the algae with protection and nutrients, while the algae photosynthesize and supply the coral wall with sugars. Cleaner fish and shrimp establish cleaning stations where larger fish come to have parasites removed, a mutually beneficial arrangement that has evolved independently in multiple ocean regions. Clownfish shelter among the stinging tentacles of anemones, immune to the venom that would kill other fish. Marine biodiversity isn't just beautiful or interesting, it's functionally essential. Each species plays a role, however small, in the web of relationships that keeps ocean ecosystems healthy. Predators control prey populations, preventing any single species from dominating. Grazers like parrotfish scrape algae from coral, preventing it from smothering the reef. Filter feeders like oysters and mussels clean water, removing particles and excess nutrients. Decomposers break down dead organic matter, recycling nutrients back into the system. The loss of even a single species can ripple through an ecosystem in unpredictable ways. When sea otter populations collapse due to hunting, sea urchins, their primary prey, exploded in number and overgrazed kelp forests, transforming lush underwater forests into barren, rocky plains. When sharks are overfished, their prey species increase, which in turn can overgraze the organisms they feed on, cascading down the food web until the entire system shifts. Tragically, marine biodiversity is declining at an alarming rate. It's estimated the ocean suffered around a 50% species loss between 1970 and 2012. Overfishing, pollution, habitat destruction, and climate change all contribute to this decline. Coral reefs are particularly vulnerable, with warming oceans causing widespread bleaching events that can kill corals faster than they can recover. Yet hope remains. Marine protected areas where fishing and other extractive activities are limited or banned have shown that ecosystems can recover when given the chance. Species rebound, coral regrows, fish populations increase. The ocean, for all the damage it has endured, retains a remarkable capacity for resilience, for renewal, for continuing the ancient dance of life that began billions of years ago in the primordial sea. Rainforests of the sea, coral reefs. Coral reefs are among the most spectacular and valuable ecosystems on Earth. Built by tiny animals over thousands of years, they rise from the seafloor in structures of limestone and living tissue, creating underwater cities of color and complexity that support an astonishing diversity of life. Though they cover less than 1% of the ocean floor, coral reefs provide habitat for approximately 25% of all marine species, making them biodiversity hotspots of global importance. The Great Barrier Reef, extending for over 2,300 kilometers along Australia's northeastern coast, is the world's largest coral reef system and the largest living structure on the planet. It's visible from space, a ribbon of life stretching along the Queensland coast, made up of over 3,000 individual reefs, coral cays, and hundreds of islands. Over 9,000 known species call it home, from tiny coral polyps to humpback whales that migrate through its waters to give birth. The biodiversity of the Great Barrier Reef is extraordinary. Around 1,600 species of fish swim among more than 600 species of hard and soft coral. 4,000 species of mollusks live there. 30 species of whales and dolphins visit or reside in its waters. 6 of the world's 7 species of marine turtle nest on its beaches. One of the world's largest dugong populations grazes in its seagrass beds. The reef supports half the world's diversity of mangrove species and vast meadows of seagrass that stabilize sediment and provide nursery habitat for countless fish. But what exactly is coral? Despite appearances, coral is not a plant or a rock. but an animal, specifically a colony of thousands or millions of tiny polyps, each one related to jellyfish and sea anemones. A coral polyp is small, often just a few millimeters across, with a soft body and a ring of tentacles surrounding a central mouth. The polyp builds a hard calcium carbonate skeleton beneath itself, a protective cup in which it sits. As polyps grow, divide, and die, they add to this skeleton, layer upon layer, year after year, building the massive limestone structures we recognize as coral reefs. The secret to coral success lies in symbiosis. Most reef-building corals house microscopic algae called zooxanthellae in their tissues. These algae photosynthesize using sunlight to convert carbon dioxide and water into sugars, much of which they share with the coral polyps. In return, the coral provides the algae with protection, nutrients, and access to sunlight. This partnership is so productive that coral reefs can thrive in nutrient-poor tropical waters, building massive structures in seas that would otherwise support little life. But this partnership is also vulnerable. Coral and algae have evolved together to survive within a narrow temperature range. When sea temperatures rise even a few degrees above normal for several weeks, the algae begin producing toxic compounds. The coral, sensing danger, expels the algae from its tissues. Without the algae, the coral loses its color, revealing the white calcium carbonate skeleton beneath, a process called coral bleaching. Bleached coral isn't dead, but it's starving. Without the sugars provided by algae, the coral must rely on feeding with its tentacles, catching plankton from the water, which provides far less energy. If temperatures return to normal quickly, the coral can recover, taking in new algae and regaining its color and health. But if warm conditions persist, the coral dies, leaving behind only its skeleton, which is gradually colonized by algae and other organisms. The Great Barrier Reef has experienced 6 mass coral bleaching events since 1998, with another occurring in 2024. Some studies suggest that about 1/3 of the reef has experienced substantial damage from bleaching, with large amounts of coral dying from heat stress, even before there was time to expel their algae. This suggests the risks from climate change are even greater than previously thought. Climate change isn't the only threat to coral reefs. Chemical runoff from agriculture carries fertilizers and pesticides into coastal waters, promoting algae growth that can smother coral. Sediment from deforestation and coastal development clouds the water, reducing the light available for zooxanthellae to photosynthesize. Overfishing removes herbivorous fish that keep algae in check, allowing seaweed to overgrow the coral. Large storms and cyclones can physically break apart reef structures. Crown-of-thorns starfish, which feed on coral polyps, occasionally explode in population and devastate large areas of reef. Despite these challenges, coral reefs provide immense value to human societies. They protect coastlines from erosion and storm damage, acting as natural breakwaters that absorb wave energy. They support fisheries that provide food and livelihoods to hundreds of millions of people worldwide. They attract tourism, generating billions of dollars annually. The Great Barrier Reef alone contributes over 6 billion Australian dollars to the economy each year and supports about 60,000 jobs. Coral reefs also contain compounds that are used to treat human ailments. Reef organisms produce unique chemicals to defend themselves from predators, fight disease, and outcompete neighbors. Some of these compounds have shown promise as antibiotics, anti-inflammatory agents, and even cancer treatments. The loss of coral reef biodiversity could mean the loss of valuable medicines we've yet to discover. Beyond economics, coral reefs hold intrinsic value. They are complex ecosystems that have existed for millions of years, evolving intricate relationships and supporting forms of life found nowhere else on Earth. A coral reef is a living library of evolutionary solutions to the challenges of survival in the sea, a testament to the creativity and resilience of life itself. Protecting coral reefs requires action at multiple scales. Locally, reducing pollution, managing fisheries sustainably, and establishing marine protected areas can help reefs recover from disturbances. Globally, addressing climate change by reducing greenhouse gas emissions is essential to prevent further warming and ocean acidification, which makes it harder for corals to build their calcium carbonate skeletons. There are also efforts to actively restore damaged reefs. Scientists are growing coral in nurseries and transplanting it to degraded areas, essentially gardening the ocean. Researchers are experimenting with breeding corals that are more tolerant to heat and acidification, hoping to create reefs that can withstand future conditions. Some projects use artificial structures to provide substrate for coral larvae to settle on, jump-starting reef recovery. Whether these efforts will be enough remains uncertain. The challenges facing coral reefs are immense, and the window for effective action is closing. But the resilience of life, the capacity for recovery when conditions improve, gives reason for hope. Coral reefs have survived ice ages, sea level changes, and mass extinctions over millions of years. With our help, they may yet survive the changes we have wrought and continue to thrive as rainforests of the sea, bright and bustling and full of wonder for generations to come. The ocean's chemistry, salt, carbon, and changing seas. The ocean is more than water. It is a complex chemical solution, a vast reservoir of dissolved minerals, gases, and organic compounds that interact in intricate ways to support life and regulate Earth's climate. Understanding the ocean's chemistry reveals how deeply interconnected all parts of our planet truly are. Seawater's most obvious chemical characteristic is its saltiness. On average, ocean water contains about 35 grams of dissolved salts per liter, roughly 3.5% by mass. Most of this is sodium chloride, common table salt, but seawater also contains magnesium, sulfate, calcium, potassium, and trace amounts of nearly every naturally occurring element. This salt comes primarily from the weathering of rocks on land. Rain, slightly acidic from dissolved carbon dioxide, slowly dissolves minerals from rocks. Rivers carry these dissolved ions to the sea, where they accumulate over millions of years. Salinity varies across the ocean. In tropical regions, where evaporation is high, such as the subtropical Atlantic and the Red Sea, salinity can exceed 40 grams per liter. In polar regions, where melting ice adds fresh water, or in areas with heavy rainfall like the tropical Pacific, salinity may drop to 30 grams per liter or less. These differences, small as they seem, are crucial for ocean circulation because saltier water is denser and more likely to sink. The ocean also holds enormous quantities of dissolved gases, particularly oxygen and carbon dioxide. Oxygen enters the ocean at the surface through diffusion from the atmosphere and as a byproduct of photosynthesis by phytoplankton. Cold water holds more dissolved oxygen than warm water, which is why polar seas are particularly oxygen-rich. This oxygen is essential for marine life, from fish to invertebrates to microbes. Areas with very low oxygen, called oxygen minimum zones, exist at mid-depths in some parts of the ocean, creating challenging conditions for animals that venture there. Carbon dioxide plays an even more complex role. The ocean absorbs about 25 to 30% of the carbon dioxide emitted by human activities each year, making it a critical buffer against rapid atmospheric warming. When carbon dioxide dissolves in seawater, it reacts with water to form carbonic acid, which then dissociates into bicarbonate and carbonate ions. This chemical buffering system helps regulate the ocean's pH, keeping it relatively stable despite the influx of carbon dioxide. However, as the ocean absorbs more and more carbon dioxide, its chemistry is changing. The ocean is becoming more acidic, a process called ocean acidification. Since the beginning of the Industrial Revolution, the ocean's average pH has dropped by about 0.1 units, from about 8.2 to 8.1. This might sound small, but pH is a logarithmic scale, so this represents about a 30% increase in acidity. Ocean acidification has profound implications for marine life, particularly organisms that build shells and skeletons from calcium carbonate. These include corals, mollusks like clams and oysters, many species of plankton, and some species of algae. As the ocean becomes more acidic, it becomes harder for these organisms to extract the carbonate ions they need to build their structures. In some cases, existing shells and skeletons can even begin to dissolve. Scientists have observed that oyster larvae are growing slower, with thinner and weaker shells, in waters with higher acidity. Coral reefs are finding it increasingly difficult to build their limestone skeletons. Some species of pteropods, tiny swimming snails that are important food for fish and whales, are experiencing shell dissolution in acidified waters. These changes ripple through food webs, affecting species that rely on shell-building organisms for food or habitat. The ocean stores far more carbon than the atmosphere. While the atmosphere contains about 850 gigatons of carbon and terrestrial ecosystems hold about 2,000 gigatons, the ocean contains approximately 37,700 gigatons, over 18 times more than land. Most of this carbon resides in the deep ocean, locked away for hundreds to thousands of years by the slow pace of thermohaline circulation. This carbon storage is partly biological. Phytoplankton take up carbon dioxide during photosynthesis, incorporating it into their bodies. When they die or are eaten, some of this carbon sinks to the deep ocean as marine snow or fecal pellets. Some is consumed and respired by bacteria and animals at depth, releasing carbon dioxide into deep waters. This biological pump transports carbon from the surface to the deep ocean, helping to keep atmospheric carbon dioxide levels lower than they would otherwise be. There's also a solubility pump. Cold water at the poles absorbs carbon dioxide readily. When this water sinks, as part of thermohaline circulation, it carries dissolved carbon dioxide to the deep ocean. As the water slowly rises in other parts of the ocean, warming as it approaches the surface, it releases some of this carbon dioxide back to the atmosphere. But because the sinking happens in localized regions, and the rising is spread across vast areas over hundreds of years, the net effect is carbon storage in the deep ocean. Another important aspect of ocean chemistry is nutrients. Nitrogen, phosphorus, iron, and silica are all essential for phytoplankton growth, but they're often scarce in surface waters, especially in the open ocean not far from land. Upwelling brings these nutrients up from the deep ocean, where they've accumulated from the decay of organic matter. In areas with strong upwelling, such as the coasts of Peru, California, and Namibia, nutrient-rich water fuels massive phytoplankton blooms, which in turn support abundant fish populations. Iron is particularly important and often limiting in the ocean. While nitrogen and phosphorus are relatively abundant in many areas, iron is so scarce in the open ocean that adding even tiny amounts can trigger large phytoplankton blooms. This has led to controversial proposals to fertilize the ocean with iron to stimulate phytoplankton growth and increase carbon uptake, though concerns about unintended ecological consequences have limited such experiments. The ocean's chemistry is not static. It changes with depth, with latitude, with season, and over geological time. It responds to atmospheric conditions, biological activity, and geological processes. And increasingly, it responds to human activities, absorbing our carbon emissions, warming with our climate, and acidifying from the extra carbon dioxide. Understanding ocean chemistry is understanding how the ocean functions, how it supports life, and how it's changing in response to the unprecedented pressures of the Anthropocene. Wonders of the abyss, life in the deep sea. The deep sea, that vast realm beyond the reach of sunlight, was once thought to be a barren wasteland, too dark, too cold, too pressurized to support life. But exploration over the past several decades has revealed a world of astonishing complexity and beauty, where life has found ways to thrive in conditions that challenge our understanding of what's possible. One of the most remarkable discoveries in deep-sea biology is the existence of hydrothermal vents. These underwater geysers occur along mid-ocean ridges, where tectonic plates pull apart and magma rises close to the seafloor. Cold seawater seeps down through cracks in the rock, gets heated to temperatures exceeding 350 degrees Celsius by the underlying magma, and shoots back up loaded with dissolved minerals and chemicals. The water pouring from these vents is toxic to most life, rich in hydrogen sulfide, methane, and heavy metals. Yet around the vents, life thrives in extraordinary abundance. Towering tube worms, some over 2 meters tall, wave their red plumes in the chemical-laden water. Swarms of white crabs and pale shrimp cluster around the vents. Clumps of mussels and clams cover the rocks. Bacterial mats carpet the seafloor, glowing faintly in the darkness. This ecosystem runs on chemistry rather than sunlight. Bacteria around the vents use a process called chemosynthesis, deriving energy from chemical reactions, particularly the oxidation of hydrogen sulfide, to build organic molecules from carbon dioxide. These bacteria form the base of the food web, much as phytoplankton do in sunlit waters. Some animals graze directly on the bacteria. Others, like the giant tube worms, house bacteria inside their bodies in a symbiotic relationship. The worm has no mouth or gut. It relies entirely on its bacterial partners for nutrition, providing them with hydrogen sulfide and oxygen absorbed through its red plume. Hydrothermal vent ecosystems support densities of life up to 65 pounds per square foot, comparable to the densest rainforests on land. They demonstrate that life is not limited to sunlight and photosynthesis, but can find energy in the chemical reactions of the Earth itself. This discovery has profound implications, suggesting that life might exist in similar environments elsewhere in the solar system, such as in the ice-covered oceans of Jupiter's moon Europa or Saturn's moon Enceladus. Bioluminescence is another wonder of the deep sea. In the perpetual darkness below 1,000 meters, the ability to produce light is incredibly valuable. About 90% of deep-sea animals possess bioluminescent organs, using them in a stunning variety of ways. Some fish use bioluminescence to lure prey, like the famous anglerfish, which dangles a glowing lure above its mouth, drawing curious fish within range of its enormous jaws. Others use light for camouflage, a strategy called counter-illumination. By producing light on their undersides that matches the faint glow from above, these animals erase their silhouette, making them nearly invisible to predators looking up from below. Still others use light for communication, flashing patterns to attract mates or coordinate with members of their species. Some squid and octopuses can create elaborate light shows across their skin, changing patterns rapidly to signal intentions or confuse predators. Certain species of shrimp have been observed producing light when disturbed, possibly to startle predators or attract the attention of even larger predators that might attack the original threat. The chemistry of bioluminescence usually involves a light-emitting molecule called luciferin and an enzyme called luciferase. When luciferin reacts with oxygen in the presence of luciferase, it produces light with very little heat, an almost perfect conversion of chemical energy into light energy. Different species use different forms of luciferin and luciferase, suggesting that bioluminescence has evolved independently many times in the history of life. Deep-sea creatures have evolved other remarkable adaptations to their extreme environment. Many have enormous eyes to capture every photon of light, whether from bioluminescence or the faint remnants of sunlight in the upper reaches of the twilight zone. Others have lost their eyes entirely, relying on other senses to navigate and hunt. Many deep-sea fish have distensible stomachs, allowing them to swallow prey larger than themselves, important in an environment where meals are rare and unpredictable. Gulper eels can unhinge their jaws to engulf prey. Black swallowers have been found with fish in their stomachs that exceed their own body size. Pressure adaptation is essential. At 4,000 meters, pressure is about 400 times atmospheric pressure. At the bottom of the Mariana Trench, it exceeds 1,000 atmospheres. Most organisms with gas-filled spaces would be crushed. But deep-sea creatures have bodies largely composed of incompressible fluids and tissues. Their cells contain special proteins and molecules that function properly under high pressure, where the proteins of surface-dwelling organisms would denature and cease to function. Metabolism in the deep sea is generally slow. Food is scarce, limited mainly to marine snow drifting down from above. So many deep-sea animals have evolved to conserve energy. They grow slowly, reproduce infrequently, and live long lives. Some deep-sea fish may live for over a century, growing very slowly but persisting in the stable, cold environment. The deep sea is also home to some of the ocean's most bizarre and least known creatures. The vampire squid, despite its name, is not a squid, but occupies its own taxonomic order. It lives at depths where oxygen is very low, conditions few other animals can tolerate, and can turn itself inside out to confuse predators. The barrel-eye fish has a transparent head, allowing its tubular eyes to rotate within the dome of its skull to look upward or forward. Deep-sea octopuses brood their eggs for over 4 years, the longest known brooding period for any animal, sitting motionless on the seafloor, guarding their eggs until they hatch. Dumbo octopuses, named for ear-like fins that resemble the cartoon elephant's ears, flutter through the water in the deepest parts of the ocean, feeding on worms and crustaceans on the abyssal plains. The deep sea remains one of the least explored environments on Earth. We've mapped the surface of Mars in greater detail than the deep ocean floor. Many of the species living there have never been seen alive. New discoveries are made regularly, from strange new jellyfish to entire ecosystems built around chemosynthetic bacteria on cold seeps, where methane and other hydrocarbons seep from the seafloor. Yet even this remote environment is not safe from human impact. Deep-sea mining threatens to disrupt ecosystems we barely understand. Fishing trawlers drag nets across the deep sea floor, destroying fragile corals and sponge gardens. Plastic debris has been found even in the Mariana Trench. The deep sea, for all its remoteness, is connected to the surface world and vulnerable to the changes we make above. The ocean's gift, climate, oxygen, and the blue engine. The ocean is not a separate system from the atmosphere or the land. It is intimately connected to both, playing a central role in regulating Earth's climate, producing the air we breathe, and maintaining the conditions necessary for life. The ocean is, in a very real sense, the engine that drives the habitability of our planet. Let's start with oxygen. More than half of the oxygen in Earth's atmosphere is produced by the ocean, specifically by phytoplankton, microscopic photosynthetic organisms that drift in the sunlit surface waters. These tiny algae, too small to see individually, collectively perform photosynthesis on a global scale, splitting water molecules, releasing oxygen, and building organic compounds from carbon dioxide and sunlight. The most abundant photosynthesizer in the ocean, and possibly the most abundant photosynthetic organism on Earth, is a bacterium called Prochlorococcus. Though it was discovered only in 1986, Prochlorococcus is now known to produce roughly 20% of the oxygen in our atmosphere. A single cell is less than a micrometer across, but there are approximately 3 trillion of them in the ocean, forming a vast, invisible forest that quietly sustains terrestrial life. Other phytoplankton, including diatoms, dinoflagellates, and cyanobacteria, contribute the rest. Together, they form the base of the marine food web and the foundation of the ocean's oxygen production. Every second breath you take comes from the sea, from organisms you'll never see, living in a realm most humans rarely consider. The ocean also regulates Earth's temperature by absorbing and distributing heat. Water has a very high heat capacity, meaning it can absorb large amounts of thermal energy without changing temperature much. The ocean has absorbed over 90% of the excess heat generated by human greenhouse gas emissions over the past 50 years. Without this buffering effect, the atmosphere would have warmed far more dramatically, making many regions uninhabitable. Ocean currents distribute this heat across the planet. Warm water flows from the tropics toward the poles, releasing heat to the atmosphere and moderating the climate of high-latitude regions. Cold water flows from the poles toward the equator, cooling tropical regions and creating upwelling zones rich in nutrients. This constant circulation of heat helps prevent extreme temperature gradients and creates the climate zones that support different ecosystems. The ocean is also central to the water cycle, the continuous movement of water between the ocean, atmosphere, and land. About 86% of global evaporation occurs over the ocean. This water vapor rises into the atmosphere, forms clouds, and eventually falls as precipitation, much of it back into the ocean, but some of it over land, feeding rivers, replenishing groundwater, and sustaining terrestrial life. Without the ocean's contribution to the water cycle, the continents would be vast deserts. The ocean provides the moisture that becomes rain and snow, that fills our rivers and lakes, that nourishes crops and forests. Even in places far from the coast, the water that sustains life often originated in the ocean, evaporated by the sun's warmth, carried inland by winds, and returned to the sea by rivers in an endless cycle. The ocean's role in the carbon cycle is equally vital. As we've discussed, the ocean absorbs about a quarter of the carbon dioxide emitted by human activities. This absorption slows the rate of atmospheric warming, but it comes at a cost. The ocean is acidifying, and its ability to absorb more carbon dioxide may be decreasing as it warms and as circulation patterns change. Phytoplankton play a crucial role in the ocean's carbon cycle through the biological pump. When phytoplankton photosynthesize, they take up carbon dioxide from the water. Some of this carbon is transferred up the food web as zooplankton, and fish eat the phytoplankton. But much of it sinks to the deep ocean when phytoplankton die or are consumed and excreted as fecal pellets. This process, repeated trillions of times every day, transports massive amounts of carbon from the surface to the deep ocean, where it can remain sequestered for hundreds or thousands of years. Seagrass meadows and mangrove forests, though they occupy a relatively small area, are extraordinarily effective at capturing and storing carbon. Seagrass is thought to absorb 35 times more carbon dioxide than rainforests per unit area. These coastal ecosystems, sometimes called blue carbon habitats, bury organic carbon in sediments where it can remain stored for millennia. Protecting and restoring these habitats is increasingly recognized as an important strategy for climate mitigation. The ocean also influences weather patterns beyond simple heat distribution. Phenomena like El Niño and La Niña, arising from changes in ocean temperatures and currents in the tropical Pacific, affect precipitation, storm patterns, and temperatures worldwide. An El Niño event can bring drought to Australia and Indonesia, flooding to South America, and altered storm tracks across the northern hemisphere. The ocean and atmosphere are so tightly coupled that changes in one inevitably affect the other. Hurricanes and typhoons, among the most powerful storms on Earth, derive their energy from warm ocean water. When sea surface temperatures exceed about 26 degrees Celsius, evaporation from the ocean can fuel the development of tropical cyclones. As the ocean warms due to climate change, there's concern that hurricanes may become more intense, carrying more moisture and producing heavier rainfall, even if the total number of storms doesn't increase. The ocean's influence on climate operates across multiple timescales. On daily and seasonal scales, it moderates temperature swings, keeping coastal regions milder than inland areas. On decadal scales, patterns like the North Atlantic Oscillation and the Pacific Decadal Oscillation shift ocean and atmospheric circulation, affecting regional climate for years or decades. On geological timescales, spanning thousands to millions of years, changes in ocean circulation have been linked to ice ages, warm periods, and major shifts in global climate. The ocean's role as Earth's climate engine is not a passive one. It responds to changes in solar radiation, atmospheric composition, and land surface conditions. But it also drives changes, feeding back into the atmosphere and influencing the trajectory of our climate. Understanding the ocean is essential for understanding past climates, predicting future changes, and managing the planet we all share. Giants and wonders, remarkable marine creatures, the ocean is home to the largest animals ever to have lived on Earth. The blue whale, Balaenoptera musculus, can reach lengths over 30 meters and weigh nearly 200 tons, more than the weight of 30 elephants. Its heart alone weighs about 400 kilograms, roughly the mass of an adult grizzly bear, and beats only 5 to 6 times per minute when the whale is diving. Its blood vessels are so large that a small child could crawl through them, though of course, this is purely theoretical. Blue whales feed primarily on krill, tiny shrimp-like crustaceans that swarm in cold, productive waters. A blue whale can consume up to 6 tons of krill per day during feeding season, gulping enormous mouthfuls of water and filtering the krill through baleen plates that hang from its upper jaw. Despite being the largest animal ever to exist, the blue whale sustains itself on some of the smallest, a testament to the productivity of the ocean and the efficiency of its food webs. The feeding strategy of baleen whales is a marvel of evolution. When a blue whale spots a dense swarm of krill, it opens its mouth to nearly 90 degrees and surges forward, engulfing up to 90 tons of water and krill in a single gulp. Accordion-like pleats in the whale's throat expand dramatically to accommodate this enormous volume. Then, using its massive tongue, which alone can weigh as much as an elephant, the whale pushes the water out through the baleen plates, which act like a giant sieve, trapping the krill inside while the water flows out. This feeding method is so energy intensive that blue whales only feed in productive waters during certain seasons. They spend summers in polar and subpolar regions where krill are abundant, building up enormous reserves of blubber that can be half a meter thick. Then they migrate toward the equator to breed and give birth in warmer waters, living off their stored fat for months without feeding. The songs of whales are another wonder. While blue whales produce low-frequency moans and pulses that can travel thousands of kilometers underwater, possibly allowing whales on opposite sides of an ocean basin to communicate, it's the humpback whales that are the true singers of the sea. Their songs are complex, structured sequences of sounds that can last from 10 to 20 minutes and are repeated for hours. Humpback whales, though smaller than blues, are perhaps the most acrobatic of the great whales. They breach, hurling their massive bodies out of the water and crashing back down in explosions of spray. They slap the water with their long pectoral fins, and they sing, producing complex songs that can last for hours and be heard hundreds of kilometers away underwater. Each population has its own song, which changes gradually over time, possibly representing a form of cultural transmission, unique among non-human animals. Scientists have discovered that humpback whale songs have structure remarkably similar to human music, with phrases, themes, and even rhyme-like patterns. All the males in a population sing essentially the same song in a given season, but the song evolves over time. New phrases are introduced, old ones are dropped, and within a few years, the song may be completely transformed. Somehow, all the males keep up with these changes, learning the new version even when separated by thousands of kilometers. Why do humpbacks sing? The songs are produced almost exclusively by males during the breeding season, suggesting they may serve to attract females or establish dominance among males, much like birdsong. But unlike most birdsong, which lasts seconds or minutes, humpback songs continue for hours without pause. A singing whale hovers motionless in the water, sometimes at considerable depth, pouring out its complex melody into the blue. Other whales have their own remarkable vocalizations. Sperm whales use a series of clicks in distinctive patterns called codas that seem to identify individuals and groups. Different sperm whale clans have different codas, forming what might be considered dialects. Belugas, the white whales of Arctic waters, are sometimes called sea canaries for their wide repertoire of chirps, clicks, and whistles. Orcas, or killer whales, also have group-specific calls that identify different pods and ecotypes. Sperm whales, the largest of the toothed whales, dive to extraordinary depths to hunt giant squid and other deep-sea prey. They can descend over 2,000 meters and hold their breath for over an hour. Their heads contain a massive organ filled with spermaceti oil, once highly prized by whalers, which may help in buoyancy control, sound production, or focusing the powerful clicks they use for echolocation. These clicks are the loudest sounds produced by any animal, reaching up to 230 decibels, capable of stunning prey at close range. Sharks, often feared but critically important to ocean ecosystems, come in astonishing variety. The whale shark, the largest fish in the ocean, can reach lengths over 12 meters and feed on plankton, filtering vast quantities of water through their gills as they cruise through tropical seas. At the other extreme, the dwarf lantern shark fits comfortably in the palm of your hand, barely 20 centimeters long, living in the deep sea and producing bioluminescent light. Great white sharks, perhaps the most iconic, are apex predators that play crucial roles in controlling populations of seals, sea lions, and fish. Despite their fearsome reputation, attacks on humans are rare. Sharks have more to fear from us than we from them. Many species are threatened by overfishing, often caught as bycatch or killed for their fins. Shark biology is fascinating in itself. Unlike most fish, sharks have skeletons made entirely of cartilage rather than bone, making them lighter and more flexible. Their skin is covered in tiny tooth-like structures called dermal denticles, which reduce drag and make their skin feel like sandpaper when rubbed the wrong way. Some species can detect electrical fields as weak as 1/1000th of a volt, allowing them to sense the muscle contractions of buried prey or navigate using Earth's magnetic field. Sharks have existed for over 400 million years, predating dinosaurs, trees, and even Saturn's rings. They've survived multiple mass extinctions and adapted to virtually every marine environment, from coastal shallows to the open ocean to the deep sea. Some species, like the Greenland shark, can live for over 400 years, making them the longest-lived vertebrates known. These slow-growing, cold-water sharks don't reach sexual maturity until they're over a century old, growing just a centimeter per year in the frigid waters of the North Atlantic and Arctic Ocean. Hammerhead sharks have heads shaped like mallets, with eyes and nostrils positioned at the ends of their cephalofoils. This bizarre head shape isn't just for show, it provides enhanced binocular vision, allowing the shark to see above and below simultaneously. The wide distribution of electroreceptors across the head functions like a metal detector, sweeping back and forth across the seafloor to find stingrays buried in the sand. Tiger sharks, named for the dark stripes visible on younger individuals, are perhaps the least picky eaters in the ocean. They've been found with license plates, boat cushions, and other indigestible items in their stomachs. This willingness to eat nearly anything makes them important scavengers, cleaning up dead animals and organic debris. They're also key predators of sea turtles, one of the few sharks with jaws strong enough to crush turtle shells. Basking sharks, the second largest fish after whale sharks, filter feed like their larger cousins, swimming with mouths agape through plankton-rich waters. They can filter over 2,000 tons of water per hour through their gill rakers, extracting tiny copepods and fish larvae. Despite their size, up to 10 meters long, basking sharks are completely harmless to humans, moving slowly and peacefully through temperate coastal waters. Sea turtles, ancient mariners that have roamed the oceans for over 100 million years, embody the ocean's connection across vast distances. Female turtles return to the exact beaches where they hatched, sometimes traveling thousands of kilometers to lay their eggs. How they navigate with such precision remains partially mysterious, though evidence suggests they use Earth's magnetic field, the angle of waves, and possibly even chemical cues. The journey of a sea turtle is one of the ocean's great epics. Hatchlings, emerging from nests buried in beach sand, scramble toward the water under cover of darkness, imprinting on the magnetic signature of their natal beach. They then disappear into the ocean, entering what scientists call the lost years, a period when juvenile turtles are rarely seen. Using currents and their magnetic sense, they navigate across entire ocean basins, feeding and growing for years or even decades. When they reach maturity, often 20 to 30 years after hatching, sea turtles begin epic migrations between feeding grounds and nesting beaches. Loggerhead turtles born in Japan cross the entire Pacific Ocean to feed off the coast of Mexico, then return to Japan to breed. Green turtles travel from Brazil to Ascension Island in the middle of the Atlantic, a journey of over 2,000 kilometers across open ocean to reach a tiny speck of land just 14 kilometers wide. The navigation abilities required for such journeys are extraordinary. Sea turtles can detect variations in Earth's magnetic field that differ by less than 1%, allowing them to create mental maps based on magnetic coordinates. They may also use sun compasses during the day and star patterns at night, integrate information about wave direction and ocean currents, and possibly even use smell to recognize chemical signatures of specific regions. Leatherback sea turtles, the largest of the 7 species, can weigh over 600 kilograms and dive to depths over 1,000 meters. They feed primarily on jellyfish, consuming enormous quantities to meet their energy needs. A single leatherback can eat more than its own body weight in jellyfish each day, helping to control jellyfish populations that might otherwise explode and outcompete fish larvae and other organisms. Leatherbacks are also among the most wide-ranging animals on Earth. They've been tracked swimming from nesting beaches in Indonesia to feeding grounds off California, from the Caribbean to the coast of Africa, from tropics to subpolar waters. Unlike other sea turtles, leatherbacks can maintain body temperatures significantly above water temperature, allowing them to hunt in cold, productive waters where jellyfish congregate. This thermoregulation is achieved through their large size, thick layer of oil-saturated blubber, and a countercurrent heat exchange system in their flippers. Sadly, all 7 species of sea turtles are threatened or endangered. They face dangers from pollution, fishing nets, coastal development, destroying nesting beaches, and climate change affecting sand temperatures, and thus the sex ratio of hatchlings. Warmer sand produces more females. Conservation efforts, including protection of nesting beaches, use of turtle-excluded devices in fishing nets, and reduction of plastic pollution, are helping some populations recover. But the journey remains precarious for these ancient wanderers. Octopuses are among the most intelligent invertebrates, capable of solving complex problems, using tools, and even displaying what appears to be playful behavior. They have 9 brains, 1 central brain, and a smaller brain in each of 8 arms, allowing each arm a degree of independent control. They can change color and texture in milliseconds, blending seamlessly with their surroundings, or flashing warning colors to deter predators. The intelligence of octopuses never ceases to amaze researchers. In laboratory experiments, octopuses have learned to open child-proof bottles, to retrieve food, navigate complex mazes, and recognize individual humans. They can observe another octopus solving a problem, and then replicate the solution, demonstrating observational learning. Some octopuses have even been observed using tools, carrying coconut shells or clam shells to construct portable shelters. Their ability to change appearance goes far beyond simple color changes. Octopuses can alter the texture of their skin to match rocky, sandy, or coral substrates. They can mimic other animals. The mimic octopus can impersonate at least 15 different species, from lionfish to sea snakes to flatfish, changing not just appearance but behavior to match whichever disguise it adopts. This shape-shifting ability is controlled by specialized skin cells called chromatophores, which contain pigment and can expand or contract rapidly, and iridophores and leucophores, which reflect light to create metallic or white colors. What makes this even more remarkable is that octopuses are colorblind. They can't see the colors they're matching. Instead, their skin may be able to sense light directly, independent of their eyes, allowing them to perceive and match colors without conscious visual processing. Research has shown that octopus skin contains the same light-sensitive proteins found in eyes, suggesting their entire body surface may function as a kind of distributed visual system. Octopus behavior can seem alien because their intelligence evolved completely independently from vertebrate intelligence. While mammals, birds, and fish all inherited their basic brain structure from a common ancestor, octopuses evolved their intelligence separately. Their nervous system is organized differently, with more neurons in their arms than in their brains. Each arm can explore crevices, manipulate objects, and even make decisions, while the octopus's central brain is occupied with other tasks. The giant Pacific octopus, the largest species, can span over 6 meters across and weigh over 70 kilograms. Despite their size and intelligence, they live only 3 to 5 years, dying shortly after reproducing. Females brood their eggs for months, refusing to leave them even to eat, slowly starving as they tend the next generation. This reproductive sacrifice is one of nature's most poignant examples of parental devotion. A female giant Pacific octopus may lay up to 100,000 eggs, attaching them in long strings to the roof of her den. For the next 6 to 7 months, she tends them constantly, cleaning them with her arms, aerating them with gentle jets of water, defending them from predators. She doesn't hunt during this time, doesn't eat at all, living off stored energy as her body slowly wastes away. When the eggs finally hatch and the tiny octopuses drift away on currents, but the mother dies, her life's mission complete. Male octopuses also die shortly after mating, their bodies programmed to shut down once they've passed on their genes. This short lifespan is puzzling, given their intelligence and learning capacity. An octopus that could live for decades would have time to accumulate enormous knowledge about its environment, potentially becoming even more formidable. But evolution has chosen a different path, optimizing for rapid growth and reproduction rather than longevity. Jellyfish, though they appear simple, are ancient and remarkably successful. They've existed for over 500 million years, predating the first fish. Some species, like the immortal jellyfish, Turritopsis dohani, can revert to their juvenile polyp stage after reaching maturity, potentially living indefinitely barring predation or disease. The immortal jellyfish's ability to essentially age backward challenges our understanding of biology. When injured, starved, or simply old, this tiny jellyfish can transform its cells back into their earliest form, settling to the seafloor and converting into a polyp, the stationary stage from which jellyfish grow. The polyp then produces new jellyfish through budding, and the cycle can repeat. It's akin to a butterfly transforming back into a caterpillar, then into a butterfly again, indefinitely. Jellyfish are not actually fish, but gelatinous zooplankton, members of the phylum Cnidaria, which also includes corals and anemones. Their bodies are about 95% water, with no brain, no heart, no blood, and no bones. They drift with currents and swim weakly by pulsing their bell-shaped bodies, which contracts to expel water and propels them forward. Despite their apparent simplicity, they're effective predators, using stinging cells called nematocysts on their tentacles to capture prey. These nematocysts are among nature's most impressive weapons. Each one is a coiled, hollow thread armed with barbs or toxins, contained in a capsule under high pressure. When triggered by touch or chemical signals, the nematocyst explodes outward in less than a millionth of a second, one of the fastest movements in nature, firing its thread into prey or predator. The threads can pierce skin, inject venom, or simply entangle the target. A single jellyfish may have millions of these stinging cells. The venom varies in potency. Most jellyfish stings are mild, causing temporary pain and irritation. But some species pack a deadly punch. The box jellyfish, found in tropical Indo-Pacific waters, possesses venom so potent that a severe sting can kill a human within minutes through cardiac arrest and nervous system failure. The Portuguese Manauai whale, technically not a true jellyfish, but a colonial organism composed of many specialized polyps, has tentacles that can extend over 30 meters and deliver excruciatingly painful stings. Lion's mane jellyfish, found in cold northern waters, are among the largest jellyfish, with bells over 2 meters in diameter and tentacles that can extend over 30 meters, longer than a blue whale. These tentacles are covered in stinging cells that deliver venom to capture prey and defend against predators. Jellyfish populations have been increasing in many parts of the world, possibly due to overfishing, removing their predators and competitors, warming oceans favoring their reproduction, and pollution creating low oxygen zones where jellyfish can thrive, but fish cannot. In some areas, massive jellyfish blooms have clogged fishing nets, stung swimmers en masse, and even shut down power plants by blocking cooling water intakes. Yet jellyfish play important ecological roles. They consume vast quantities of zooplankton and small fish, controlling populations and channeling energy through the food web. They provide food for sea turtles, sunfish, and some seabirds. Some small fish live among jellyfish tentacles, immune to the stings, using the jellyfish as mobile shelter. And in death, sinking jellyfish bodies transport carbon and nutrients to the deep ocean, supporting communities that would otherwise receive little food. Manta rays, with wingspans exceeding 7 meters, glide through tropical waters like underwater birds, filtering plankton and small fish from the water. Despite their size, they're gentle giants, often curious about divers and even appearing to recognize individual humans. They possess the largest brains of any fish relative to body size and display complex social behaviors. The ocean sunfish, or mola mola, is one of the strangest fish in the sea. It's essentially a giant head with fins lacking a proper tail. Adults can weigh over 2 tons, making them the heaviest bony fish. They feed primarily on jellyfish, requiring enormous quantities to meet their energy needs, and spend time at the surface, appearing to sunbathe, though they may actually be allowing seabirds to pick parasites from their skin. In the deep sea lives the oarfish, the longest bony fish in the world. With its ribbon-like body reaching lengths over 17 meters, its red dorsal fin running the length of its back, and its horse-like face. The oarfish is likely responsible for many sea serpent legends. It lives at depths between 200 and 1,000 meters and is rarely seen alive, occasionally washing ashore after storms. These remarkable creatures, from the immense to the bizarre, remind us that the ocean is home to forms of life that challenge our imagination. They've evolved solutions to survival that differ radically from anything on land, shaped by the unique conditions of the marine environment. Each one plays a role in the ocean's ecology, from the smallest krill to the largest whale, from the tiniest plankton to the strangest deep-sea fish, all connected in the vast web of life that fills the sea. Our ocean, our responsibility. For all its vastness and power, the ocean is vulnerable. Human activities, fishing, pollution, coastal development, climate change are altering the ocean faster than at any time in human history, and possibly faster than at any time in millions of years. Understanding these threats and our capacity to address them is essential for the future of both the ocean and ourselves. Overfishing is one of the most immediate threats. The Marine Stewardship Council's 2024 report highlighted that 37.7% of monitored marine fish stocks were being overfished in 2021, an increase from previous years. When we remove fish faster than they can reproduce, populations collapse. This happened dramatically with Atlantic cod in the 1990s, when overfishing drove what had been one of the world's most abundant fish to near commercial extinction. The collapse of Atlantic cod fisheries off Newfoundland serves as a stark warning. For centuries, these waters teemed with cod. Early explorers reported fish so abundant you could lower a basket into the water and pull it up full. The fishery sustained communities, cultures, and economies. But improved fishing technology and increased demand led to catch rates that exceeded the cod's ability to reproduce. By the early 1990s, the population had crashed by over 99%. Canada imposed a moratorium on cod fishing in 1992, putting 40,000 people out of work. 30 years later, the cod have still not fully recovered, and the ecosystem has shifted to a new state dominated by different species. Overfishing doesn't just harm the targeted species, it disrupts entire ecosystems. When predators are removed, their prey can explode in number. When prey species are removed, predators starve. And roughly 40% of global marine catches consist of bycatch, non-target species caught accidentally and often killed, including sea turtles, dolphins, sharks, and seabirds. Bycatch is a massive problem that receives less attention than it deserves. Shrimp trawls can catch 10 pounds of bycatch for every pound of shrimp landed. Longline fishing for tuna and swordfish hooks, albatrosses, sea turtles, and sharks. Drift nets, sometimes called walls of death, can stretch for kilometers and catch anything in their path. Millions of tons of marine life are wasted each year, thrown back dead or dying, their populations depleted for no purpose. Some species are particularly vulnerable. Bluefin tuna, prized for sushi and capable of fetching tens of thousands of dollars for a single fish, have been overfished to a fraction of their historical numbers. Some shark species, slow growing and producing few young, have declined by over 90% in parts of their range. Rays and skates, caught as bycatch in bottom trawls, face similar pressures. Pollution takes many forms. Plastic waste is perhaps the most visible. Millions of tons of plastic enter the ocean each year, from bottles and bags to microplastics so small they're barely visible. The Great Pacific Garbage Patch, a massive accumulation of plastic debris between Hawaii and California, is estimated to be twice the size of Texas. Marine animals ingest plastic, mistaking it for food, or become entangled in larger debris. Plastic breaks down into ever smaller pieces, but never truly disappear, accumulating in the food web and potentially affecting even the fish we eat. Plastic pollution affects wildlife in heartbreaking ways. Sea turtles mistake floating plastic bags for jellyfish, their favorite food. Seabirds feed plastic fragments to their chicks, filling their stomachs with indigestible material until they starve. Whales have been found dead with hundreds of pounds of plastic in their stomachs. Even in the deepest trenches, amphipods have been found with microplastics in their guts. There is nowhere in the ocean untouched by plastic pollution. The chemical composition of plastics adds another layer of concern. Many plastics contain additives like plasticizers, flame retardants, and stabilizers, some of which are toxic or hormone disrupting. As plastics break down in seawater, these chemicals can leach out. Microplastics can also absorb other pollutants from the water, concentrating toxins that then enter the food web when the plastic is consumed. Chemical pollution from agricultural runoff, industrial discharge, and oil spills degrades water quality and harms marine life. Fertilizers cause algae blooms that deplete oxygen when they decay, creating dead zones where few animals can survive. The Gulf of Mexico has a seasonal dead zone the size of New Jersey caused by nutrients flowing down the Mississippi River. These dead zones, formerly called hypoxic zones, occur when excess nutrients fuel massive algae blooms. When the algae die and decompose, bacteria consuming the dead matter use up dissolved oxygen faster than it can be replenished. Fish and mobile animals flee, but bottom-dwelling creatures like clams, crabs, and worms often suffocate. Dead zones are expanding worldwide, from the Baltic Sea to the East China Sea, from Chesapeake Bay to the coast of Oregon. Hundreds of dead zones now exist globally, affecting hundreds of thousands of square kilometers of ocean. Oil spills, though less common than chronic pollution, can be catastrophic when they occur. The Deepwater Horizon spill in 2010 released nearly 5 million barrels of oil into the Gulf of Mexico, coating beaches, killing wildlife, and contaminating food webs. Cleanup efforts, including the use of chemical dispersants, may have caused additional harm. Studies continue to document impacts on fish reproduction, dolphin health, and deep-sea coral communities years after the spill. Climate change is perhaps the most pervasive threat. The ocean has absorbed over 90% of the excess heat from greenhouse gas emissions, but this warming is having profound effects. Coral reefs are bleaching. Marine species are shifting their ranges toward the poles or into deeper, cooler water. Sea ice is melting, affecting species from polar bears to krill. Ocean circulation patterns are changing in ways that could have far-reaching consequences. The warming ocean is measurable and accelerating. Since the 1950s, the ocean's heat content has increased dramatically. This absorbed heat causes thermal expansion, contributing to sea level rise even before ice melt is considered. Warmer waters hold less dissolved oxygen, creating additional stress for marine life. And as the ocean stratifies, warm water floating on cold, vertical mixing decreases, reducing the transport of nutrients from deep to surface waters. Marine species are responding to warming in various ways. Many fish species are shifting their ranges poleward, following their preferred temperature zones. In the North Sea, cold water species are being replaced by warm water species from farther south. In the tropics, some fish are moving to deeper, cooler water, but not all species can move, and not all movements lead to success. Coral reefs cannot migrate. Bottom-dwelling organisms are limited by substrate availability, and as species ranges shift, new, competitive, and predatory relationships form with unpredictable consequences. Rising sea levels, caused by thermal expansion of warming water and melting ice sheets, threaten coastal communities worldwide. Many island nations face the possibility of disappearing entirely beneath the waves. Major cities, home to hundreds of millions of people, will need to adapt to higher sea levels and more frequent flooding. Current projections suggest sea level could rise by 0.5 meter to 1 meter by 2021, with potentially much greater rises if major ice sheets in Greenland and Antarctica destabilize. Even 1 meter of rise would inundate low-lying areas, contaminate freshwater sources with salt water, increase storm surge damage, and force millions to relocate. Small island nations like the Maldives, Tuvalu, and Kiribati could become uninhabitable. Coastal megacities like Miami, Shanghai, and Lagos face increasing flood risk. Despite these challenges, there are reasons for hope. Marine protected areas, where human activities are limited, have shown that ocean ecosystems can recover remarkably quickly when given the chance. In well-managed protected areas, fish populations rebound, corals regrow, and biodiversity increases. Some countries have protected large portions of their ocean territory, creating sanctuaries where marine life can thrive. The recovery potential is real and documented. After the establishment of no-take marine reserves in New Zealand, studies showed fish biomass increased by an average of 224% within 5 years. Coral cover increased in protected areas in the Philippines. Seal and sea lion populations rebounded along the California coast after protection. Even small reserves can have disproportionate benefits, serving as sources of larvae that replenish surrounding areas. Sustainable fishing practices, including catch limits, gear restrictions, and seasonal closures, can allow fish populations to recover while still supporting fishing communities. Consumer choices matter too. Choosing sustainably caught fish and reducing consumption of overfished species creates market pressure for better practices. Some fisheries have successfully rebuilt after near collapse. Striped bass along the US Atlantic coast recovered after strict management measures. Haddock, Atlantic halibut, and some flounder stocks show signs of recovery where fishing pressure has been reduced. These success stories demonstrate that with political will and proper management, we can restore depleted fish populations. Reducing pollution requires action at every level. Individuals can reduce plastic use, properly dispose of waste, and support policies that limit pollution. Governments can regulate industrial discharge, improve wastewater treatment, and invest in clean energy. Communities can organize beach cleanups and advocate for stronger environmental protections. Innovation offers additional hope. Scientists are developing biodegradable plastics from seaweed and other renewable materials. Ocean cleanup technologies are being deployed to remove existing plastic from the water. Improved agricultural practices reduce fertilizer runoff. Renewable energy reduces the need for offshore oil drilling. Each advance represents a step toward a healthier ocean. Addressing climate change requires global cooperation to reduce greenhouse gas emissions, transition to renewable energy, protect and restore natural carbon sinks like seagrass beds and mangrove forests, and help vulnerable communities adapt to changes already underway. The transition to renewable energy is accelerating. Solar and wind power are now often cheaper than fossil fuels. Electric vehicles are becoming mainstream. Energy efficiency is improving. While the pace of change needs to accelerate dramatically to avoid the worst impacts of climate change, the trajectory is encouraging. Scientists continue to study the ocean, discovering new species, mapping unexplored areas, and improving our understanding of ocean processes. Each discovery deepens our appreciation for the ocean's complexity and importance. Each advance in ocean science provides tools for better management and conservation. Recent technological advances have revolutionized ocean science. Autonomous underwater vehicles can survey the deep sea for months without surfacing. Satellite sensors track ocean temperature, color, and height with unprecedented precision. DNA sequencing allows scientists to catalog biodiversity from water samples without even seeing the organisms. Machine learning helps analyze vast datasets to detect patterns and predict changes. These tools are revealing an ocean more dynamic, more interconnected, and more vulnerable than we previously understood. The ocean has shaped human history, providing food, transportation, inspiration, and livelihoods for countless generations. It has absorbed our wastes, buffered our climate, and sustained the conditions necessary for life on land. Now, the ocean needs us to reciprocate, to recognize our dependence on its health, and to act with the wisdom and foresight necessary to preserve it for future generations. We are all connected to the ocean, even those who live far from any coast. The oxygen we breathe, the climate we depend on, the rain that falls on our crops, all derive from ocean processes. The ocean is not separate from us. It is part of the same interconnected system that includes the atmosphere, the land, and all living things. This interconnection has profound implications. A fisherman in Indonesia, a farmer in Iowa, a factory worker in Germany, and a software engineer in Japan all depend on and affect the ocean. Our choices about energy, food, transportation, and consumption ripple through global systems, ultimately influencing ocean health. Recognizing this connection is the first step toward making better choices, The ocean offers solutions as well as challenges. Offshore wind farms can generate clean energy. Seaweed aquaculture can produce food, biofuels, and animal feed while absorbing carbon and nitrogen. Tidal and wave energy could provide reliable, renewable power. The ocean, if managed wisely, can be part of the solution to climate change, food security, and sustainable development. Indigenous and local communities who have depended on the ocean for generations offer valuable knowledge about sustainable resource use, seasonal patterns, and ecosystem health. Their traditional ecological knowledge, accumulated over centuries of close observation, complements scientific understanding and can guide management decisions. Protecting the ocean requires not just science and policy, but also respect for these long-standing relationships between people and the sea, the endless blue. As we drift toward the end of this journey, let's take a moment to reflect on what we've explored. We've descended from sunlit surface waters, through twilight and midnight zones, to the deepest trenches. We've traced the path of ocean currents that circle the globe. We've met creatures from the largest whales to the smallest plankton, from bioluminescent deep-sea fish to coral polyps building reefs. We've examined the ocean's chemistry, its role in climate, and the threats it faces. The ocean remains one of Earth's great frontiers. Less than 20% has been mapped with the same detail we have for the Moon or Mars. 91% of ocean species are estimated to be undiscovered or unclassified. New hydrothermal vents, new seamounts, new species are found regularly. There are mysteries in the deep sea, in the twilight zone, even in coastal waters we thought we knew well. But even with so much left to discover, we know enough to understand that the ocean is essential, that it's changing, and that we have both the capacity and the responsibility to protect it. The ocean's health and humanity's future are inseparable. What we do to the ocean, we do to ourselves. If you've made it to the end of this journey still awake, I hope you found something that sparked curiosity or wonder. If you're drifting off to sleep, I hope your dreams are filled with blue water and strange creatures, with the gentle pulse of currents and the quiet beauty of the deep. The ocean has been flowing for billions of years. It cradled the first life. It shaped our planet. It continues to sustain us, and it will endure, adapting and changing long after we're gone. Though what form it takes, whether vibrant and full of life or degraded and diminished, depends greatly on the choices we make now. Thank you for joining me on this exploration. If these gentle dives into knowledge help you unwind, consider liking and subscribing to Whispered Knowledge. It helps others find their way here, one sleepy, curious soul at a time. Rest well. Dream of the deep blue. And remember that with every breath, you're connected to the ocean, part of the same ancient cycle of water, air, and life that has sustained our world for longer than we can truly comprehend. Good night.